Today, we're going to talk about section 3.4. This is the chain rule. We've now talked about a bunch of shortcut derivative formulas. Yesterday we talked about the product rule and also the quotient rule. Those are the rules that we have to use when we differentiate products or quotients. The chain rule is maybe the most important derivative formula that we use, and we should definitely know it. But it's also maybe the hardest to use. The chain rule is what we want in order to differentiate. It's not only what we want, but it's what we need in order to take the derivative of a composite function. So in other words, if I want to do the derivative of f of g of x, right, here's my composite function that I'm trying to differentiate. You should read the statement of the chain rule in the book. This is just the shorthand version of it. But to do the derivative of f of g of x, you take the derivative of the outside function, you evaluate it at the inside function, and then you end up multiplying by the derivative of the inside function. Again, read the textbook for this. I imagine we'll talk about it more next in-class time, but this is an important rule to remember. Whenever you have a composite that you have to differentiate, this is the formula that you have to use, the chain rule. Let's do some examples. Let's say that capital F of x is equal to the square root of x to the 4 plus 2. In chapter 1, we talked about composite functions, and I said we have to be able to recognize them. Given two functions, we have to be able to compose them, but given a composite itself, we have to be able to decompose it into the two functions that make it up. And so here, my inside function, okay, I'm going to call it lowercase g, using the notation from the formula. My inside function is x to the 4 plus 2. My outside function is the last function that's being done here. In other words, it's the square root function. So my outside function is lowercase f of x equals square root of x. In the formula for the chain rule, I see that I need the derivative of the outside function, f prime, and I also need the derivative of the inside function, g prime. So let me compute those two derivatives separately. The derivative of g of x is easy enough to do. G prime of x is equal to 4x cubed plus 0, because the derivative of 2 is 0. Likewise, we know that square root of x is x to the 1/2, and so we can do the power rule to get its derivative. F prime of x is equal to 1/2 x to the minus 1/2. All right, so these are my two derivatives of the inside and outside functions separately. For capital F prime, in other words, for the derivative of this composite function, from the chain rule now, right here, I have to do f prime of g and then times g prime of x. And so what does that look like? Well, I know what f prime is, I know what g prime is. The only thing I have to be a little bit careful about here is, for f prime, what do I want to plug in? I want to plug in g of x, not just x. My formula for f prime right now has me plugging in x, but I need it to be the original inside function, g of x. So I should take x to the 4 plus 2 and plug that into the derivative of f. And so what does it look like? It looks like this. 1/2 quantity x to the 4 plus 2, which is the original g function, raised to the negative 1/2 power. Okay, this is f prime of g of x. And then I have to multiply by g prime. G prime is just 4x cubed. There's our derivative. We're going to do a couple more chain rule problems. Next example. Suppose capital F of x is equal to x to the 5th minus x, all raised to the 50th power, right? One thing that you could do, and I would not suggest this, is you could multiply x to the 5th minus x times itself 50 times. Okay, and see what you get. You'll get a whole bunch of powers added together, subtracted, and then you could do a whole bunch of power rules, but that would be a mess. You don't want to do that. So instead you need a simpler way to compute this. Again, this capital F function is a composite. All right, the inside function is inside the parentheses. So that's, we're calling it g of x. That's x to the 5th minus x. The outside function is the 50th power function. Our notation for the outside function is lowercase f, and so that's x to the 50. The inside and outside functions here can both be differentiated very easily, and then I'll have to put them together in the correct way to get the derivative of the composite. So, g prime of x is equal to 5x to the 4 minus 1, and capital F prime of x is equal to 50 x to the 49. So, what I want to do, what I need to do here is compute capital F prime of x. In other words, I need to do the derivative of x to the 5th minus x to the 50th power. I have to use my chain rule to do this because it's a composite function. The chain rule right here tells me that I should get f prime of g of x and then times g prime of x. So, just like the last example, I know f prime of x is 50x to the 49, but that's not what goes inside f prime for the chain rule. What goes in f prime for the chain rule is the original inside function. So that is 50, and then times not just x, but g of x, which is x to the 5 minus x, all raised to the 49, and then times g prime, which is the derivative of the inside. So times the quantity 5x to the 4 minus 1. Once you get the hang of the chain rule, these are actually quite easy to do. Here's a real quick example. Let's say that capital F of x is x cubed minus 1 to the 17th power. If I want to know capital F prime, what do I do? Well, I have to do the chain rule, but I'll do it quickly here for us. What's going to happen? I differentiate the outside, which is the power function. So the 17 comes down, the new exponent is 16. The chain rule tells me I have to leave the inside function alone at first. So I have the same inside function here. The other thing that the chain rule tells me is that I should then multiply by the derivative of the inside, which is 3x squared. So there it is. Okay, again, once you get the hang of the chain rule, this is probably something that you'll be able to do real quickly. I think I have a couple more examples. Let's say capital F of x is e raised to the x squared plus 3. You need to be able to recognize this also as a composition. The inside function is the first function that's being done. In other words, the exponent here. So our g of x is x squared plus 3. The outside function is the last function being done. In other words, e raised to whatever that inside is. And so our outside function f of x is e to the x. You should be able to check then that capital F is exactly f of g of x. And it's that particular composite. With the chain rule, I need both derivatives. The derivative of g is g prime equals 2x. The derivative of e to the x, right, by now we like this one quite a bit. F prime of x is e to the x, just itself. So, if I go to compute the derivative of f prime, in other words, the derivative of e to the x squared plus 3, what do I get? I get f prime of g of x times the derivative of the inside, and now we can construct this. F prime of x is e to the x, but I need f prime of g. So we're going to take x squared plus 3 and plug it in to f prime. So that'll be e to the x squared plus 3. And then I have to multiply by g prime. G prime was 2x. There it is. These problems with e raised to a function also turn out to be common, but easy to handle once we get the hang of it. For example, if our function f of x is e to the 5x to the 4th, the derivative with the chain rule is going to be the derivative of the outside. The derivative of e is e itself. And then we plug the original back in. Right? So I get the original function here. I get e to the 5x to the 4th. But then by the chain rule, I have to multiply by the derivative of the upstairs, the derivative of the inside function, and that's 20x cubed. One more example. In class, last time, we talked about the product rule and we talked about the quotient rule. Sometimes, when we're doing the chain rule, we might also have to use the product rule or the quotient rule. Okay, our shortcuts for derivatives are very useful, right? They allow us to not have to compute limits, but with some functions, we have to do more than one rule. Here's an example. Capital F of x is equal to x times x cubed minus 1 to the 20th power. The big picture here with this function is that this is a product. Okay, to compute f prime of x, in other words, the derivative of x times x cubed minus 1 to the 20, I need to do the product rule first of all, because I have one function x times a second function. I have two different factors here. So what did the product rule tell me? The product rule tells me do the derivative of the first one, the first factor, multiply by the original second factor, and then add the first factor, and then times the derivative of the second factor. Okay, make sure you memorize the product rule. So now I can try to do these derivatives. The derivative of x is 1. It's being multiplied by the second factor. And then I'm adding. What am I adding? I'm adding x times the derivative of x cubed minus 1 to the 20. For this derivative here, I need the chain rule. But it's an easier one to do, just like I did on the front board a second ago. For the chain rule in this term, because I'm doing the derivative, I have to differentiate the outside function. The outside function is the 20th power function. So that 20 comes down. My new exponent is 19. The chain rule tells me to leave the inside function alone at first. And then at the end, we multiply by the derivative of the inside function. So that's 3x squared. Okay, all together, that's the derivative of x times the quantity x cubed minus 1 to the 20th power.